All right, today we're going to talk about mechanical work. The purpose of an engine is to give us work. We put fuel in, we get work out. So we're going to learn a little bit out today exactly what that means and how to calculate it. So work is not just a force, but it's a force exerted over a distance. Right? I'm not doing any work right now. I sure don't look like I'm doing work, right? So to do work, I actually have to exert force over distance. I need to push this furniture back some distance. And you've experienced this too. When we're walking on a hard surface, you can't see the floor here, but it's nice and firm, you're actually not doing any work at all. But let's say you're running on loose sand where every footstep it sinks into the sand. You're doing work. And the further you sink, the more work you're doing. Similarly, I bet you've noticed walking through deep snow is a lot of work. It's no big deal to take a 2-mile stroll on a sidewalk, but when you're walking through deep snow, 2 miles can be a lot of work. So work is not just force. Work is equal to force times a displacement x. And if the force and the displacement are in the same direction, then the work is greater than 0. If they're opposed, then the work is less than 0, right? Things can do work on you. You can do work on a spring, for example, and it might be negative. If the force and displacement are perpendicular, you're not doing any work at all. Right? If I push down on this table and it moves sideways, it wasn't me who moved it anyway. Right? So to express this more succinctly using vector notation, work is the force dotted with the displacement vector. Right? Both force and displacement not only have magnitudes, they have directions. Now, if I drop the vector sign, it just means we're assuming things are collinear. Very important equation. Let's put a box around it. If you're not that comfortable with vectors and the dot product, an alternative formula is the magnitude of f times the magnitude of x times cosine of the angle between them. And that's why you see that if f and x are orthogonal, and thus theta is 90 degrees, that work is 0. All right, so let's take a look at a very simple example. Let's say we've got an escalator, and we've got a sad person who at the bottom, he takes a ride up on the escalator, has a lot of fun, doesn't have to exert himself very much, and he's happy by the time he gets to the top. All right, so first of all, was this positive work or negative work done on this person? And you think, okay, well, the displacement was up and to the side. There are two components to it. We can write it as the escalator vector, or we can break it into a horizontal and vertical vector that add up to our escalator vector. And so the displacement is this way, but the force of gravity that the escalator exerted on the person, the force that opposes gravity was straight up. Gravity pulls down on the guy, so the escalator pushes straight up. So the force vector is up. Since the force and the displacement are less than 90 degrees, that means work is positive. The cosine of theta will be positive. And it also means that only the vertical displacement matters. The dot product of the force gives you because it's vertical, gives you the vertical component of displacement. So it's his weight times the vertical displacement that equals the actual work. Now, in real life, force is usually not so simple and constant. All right, that's the general case. If that force varies, let's say it looks like this. We take a little piece of that displacement, just the displacement from here to here. Just a little bitty displacement. We'll call it delta x. And the force, if delta x is small, doesn't change all that much. So we get a little bit of work. Equals that force times a little bit of displacement. And we say, okay, cool. I'll just repeat that process over and over and over. And add up all the little chunks of work into the big summation of work. So if we let delta x go to 0, this really is like a derivative. And we'll just integrate both sides. That's all there is to it. And if you hadn't noticed, since work is a product of force, units of newtons, displacements measured in meters, then we have Newton meters for the units. This is also same as a joule. So let's do an example. Let's say we've got a surface, floor, and we've got a spring attached to our surface. And this spring exerts a force that is proportional to some distance x. X is actually its displacement from the equilibrium position where it exerts 0 force. So if I want to find out the work to compress this spring, it's going to equal the integral of kx times dx from, let's just call it two positions, position 1 to position 2. All right, well, that integral is just equal to so the integral of k dx is x squared over 2. All right, x dx is x squared over 2, and the k is just a constant, so it's along for the ride. Sorry, it's 1/2 x squared over 2. So this gives you your work. So the amount of work is nonlinear. Now, let's do something a little more complicated. We're going to be working with fluids a lot. In most engines, fluid is an important part of the engine's functioning. And fluid's a general term. It's not just a liquid. A fluid is a gas, too. So gasoline engines, diesel engines, gas turbines, all these engines flow lots of gas through them. And they operate often at very high internal pressures. And here's why. Because a force is created when a pressure acts on an area. Now, you might wonder, why is area a vector? The concept just is, if I've got a planar area, here it's a rectangle, that area vector points out perpendicularly from our plane, and its magnitude is equal to the amount of surface area of our plane. So area is measured in meters squared. Pressure is measured in newtons per meter squared. So, of course, the force has units of newtons, just like it should. And the direction of the force is perpendicular to the area. So let's do an example. Let's say we've got a piston and a cylinder. And here's our fluid, and in the middle we've got some fluid pressure pushing on the underside of our piston. And of course, remember, there's atmospheric pressure pointing on the other side. We're going to neglect the weight of the piston for a moment. So the net force is the difference between these two pressures. The fluid pressure is usually a lot higher than atmospheric. And this is just the gauge pressure. This is just how high is the pressure in the fluid above atmospheric. Now, we understand that work is a force times a displacement. But let's look at what happens here to displacement. Let's say our piston, and it's got a roughly circular face. It's got some area A, this little vector. Let's say it moves up some small distance dx. To a new position. Notice that when that area moves up a little dx, it sweeps out a volume. That's the volume here in this cylinder. a little volume, so we'll call it dV. Equal to the dot product of the area and the differential displacement. So let's just remember that little fact. All right, so when we come back over here and we say our work is force times this small displacement, we go, well, that force is pressure times area. That's the force. So this gives us the work, but we're going to recognize this product, AdX, is actually a change in volume. So when you're dealing with compressing or expanding a fluid, the work you do is actually proportional to the change in volume. And if we just integrate both sides of this, we get our very important relationship Right. This is the equivalent of the saying that work is integral of f dx. This is just a convenient form when dealing with compressing with fluids. And I'll give you a quick example. Where we use this expression. And we're going to assume we're dealing with an ideal gas. Ideal gases are gases that are relatively low densities, usually, to keep it simple. So air here in this room, pretty well described by the ideal gas model. So we've got pressure times the volume in RT. N is the number of moles. This is the universal gas constant. Absolute temperature. Right, so it's got to be Kelvin, not centigrade. This is absolute pressure. Cannot use gauge pressure here. And V is the volume. We explained in our earlier derivation that there's also pressure acting outside from the atmosphere, so we're subtracting that off to give a gauge pressure here. This just comes from the ideal gas law. And we get work is equal to, and at this point it's nice to separate these two. Right? You can do that with an integral. No big deal. And I'll just write the final answer over here. The n is a constant because our number of moles isn't changing. We're not generating gas. R is a constant. It's the universal gas constant. We assumed isothermal. Here, we're going to assume constant temperature, so that's a constant. So this just becomes nRT times the integral of dV over V. And so that is just the log of V. All right, so that is the first integral. And then the second integral, P atmospheric's a constant, so we just have the integral of dV, which is V. And if you want, you can simplify this expression, since log V2 minus log V1 is the log of V2 divided by V1. But you get the basic idea. So that's how we calculate the net work done in expanding an isothermal gas. All right, thank you very much. That's it.